Assalamualaikum warahmatullahi wabarakatuh. My name is Ameer bin Basree and my supervisor is Dr. Khairul Fadzli bin Samat. Today I will present about simulation analysis on power generator of thermoelectric generator device based on Electrodeposited nanocomposite. My introduction. The thermoelectric generator, also we know as TEG, we also know as a seaback generator. Thermoelectric generator operate like heat engine, but they are less bulky and have no moving part, transforming thermal energy directly into electrical energy. Good thermoelectric properties of the material, typical of a provide significant improvement in the efficiency of the device. My problem statement is power costs are rising. Environmental pollution and global warming are issues we are dealing with at this moment. How the calculation of power generated on the moderate TEG device will be carried out and the value for possible apply nanocomposite properties. And the third is we are also need to predict the temperature difference when the TEG device is embedded with the investigate the nanocomposite. My objective is first evaluate the temperature difference can be harvested from TEG device that embedded with Bi2TE is a nanocomposite material to apply the dynamic flow parameter in the fluid simulation to calculate of power generated on the model TEG device. My literature review. Years 2019, Syed Mohsen Porki and Muhammad Hossein Ahmadi. The title is Thermoelectric Cooler and the Thermoelectric Generator Device, a review of present a potential application, modeling and material. The summary generates electrical current directly from a temperature difference, increasing the production of energy in line with industry development, transportation and life quality improvement. So, year 2030, Suhana binti Muhammad Said and Mazduki Haji Hassan. A review on thermoelectric renewable energy, principal parameter that affect their performance. Thermoelectric device can convert thermal energy from a temperature gradient into electrical energy. The importance of this parameter is universally recognized. It's an established ubiquitous routinely used tool for material device equipment and process characterization both in thermoelectric industry and in research. Miguel Mota Prego Rosmaninho, 2014, deposition of bismuth telluride nanomaterial from thermoelectric generator. Is a semiconductor which when alloyed when antimony or selenium is an effective thermoelectric thermoelectric material for cooling or portable power regeneration. Bismuth telluride is the material with the highest reactive value near room temperature, which makes it the most commonly used material in the thermoelectric market. Again, 2014 Miguel Mocha Prego Rosmaninho electroposition of bismuth telluride nanomaterial from thermoelectric generator. The model here is makeups use distribute physics that include of the following: Thomson effects, temperature dependence, mass, joule, heat, thermal resistance, seatback effect, and electrical resistance. 2017, according Grazioli and M. Mazziresi, 2017, modeling, fabrication, and experimental testing of an heat-sink-free wearable thermoelectrical generator. Thermoelectrical paste of stoichiometric, antimony telluride, and bismuth telluride were prepared, characterized, and used as active material to fabricate a flexible heat-sink-free thermoelectrical generator. The model was designed to be coupled to a 18 M voltan startup input voltage full electrical DC to DC converter. 2018 Roche and Wang comparison and parametric study of two theoretical modeling approach based on NA to water thermoelectrical generator system. Numerical model and thermal resistance model are two commonly used modeling approach to analyze and performance of thermoelectric device. This work present a steady state and fluid thermoelectrical multi-physical numerical model and improve the conventional thermal resistance model to investigate the performance of an air-to-water thermoelectric generator system. 2011, C.S. Liu and Y. Yang, a review thermoelectric research, recent development, and potential for sustainable and renewable energy application. The summary is also come to conclusion that the thermoelectric application with the current convention essentially are economic and technical for the micro small application. However, it will be transformed more significant green energy solution for improving the current environment and energy issue by using large scale thermoelectric application. 2018 Sunti Pewonga. Thermoelectric properties of lead telluride is PBTE. Lead telluride is a compound of lead telluride. The value of seabed coefficient and the electrical resistivity, thermoconductivity, and dimension figure merit are about negative 216 for the seabed coefficient. For the Tm ohm, the electrical resistivity for the thermal conductivity is 0.5, and the dimension figure merit is about 0.35 respectively at 420 Kelvin. For the Saji Ahmad 2040 is improved thermoelectrical performance of hot press non-structural and type using silicon germanium bull alloy. Silicon germanium alloy SIGE have been used in thermoelectric generator for a deep space mission to convert radioisotope heat into the electricity. The optimized sample has been a Seebeck coefficient is 284. The resistivity is 45 ohm, and the thermal conductivity is 0.93 watt at 1073 Kelvin. This is my methodology. This is my flow chart. First, I start and identify problem statement, determine objective and scope, review data collection, and develop concept design the project. My research activity, and that's my TE model. That's my model that I drawing at SolidWorks. Okay, this a step from drawing into the simulation. First, we drawing every part at the SolidWorks, and we using the SolidWorks because we can drawing is part by part, and then we assembly at the SolidWorks. When from the SolidWorks, we open the NCs, we set the material properties, and we can insert the project from the SolidWorks into the NCs, and then check the detail. Uh, we we set the detail what we going to do for that material, and then after that we can run and solve, and we can get the temperature difference, heat absorb, heat junction, current, and total current density. Okay, this is my nanocomposite that will be had in my in my simulation. First, we can see is a bismuth telluride. For the second one, antimony telluride. Antimony telluride we using for the M type. For the N type, we using the bismuth telluride, nickel bismuth telluride, lead telluride, and silicon germanium. Okay, this is my last page. This is about Seebeck coefficient, thermal conductivity, electrical resistivity. This data I must collect from my material to put in NCs to running to get the for the heat joule to get the change of temperature. This is the description about the formula and expected result. Then I think I will get to first I want to obtain the result change of every material to calculate the power input, because from the change of temperature we can input into the conclusion into our equation. Secondly, to obtain the result, compare the power output from there, so we can know from the this nanobreaker which one is going to be the best material. And lastly, to compare small result with software analysis, I will going using the ANSYS for simulation analysis. Okay, that's all for me. Thank you.